right, hi everybody. I just have a few quick announcements to make about Test 2, and I thought that this could be a substitute for the review that we normally do in class, and so here we go. Let's just dive right into it. This is Test 2 reviewed. Now, Test 2 is on 3 chapters. It's on Chapter 33, Chapter 20, and Chapter 22. I'm not going to review Chapter 22 because we've just barely started it, and we're going to be talking about it even more on Monday. So this is just a review of the first 2 chapters, 33 and 20. Chapter 33 is on ray optics. By the way, you can download this PDF from the Sakai site under Resources and the folder Test 2. So here we go. So chapter 33 is on ray optics. The first major law that we learned was the law of reflection. So if a light comes in and hits some sort of mirror-like surface like this, it's going to reflect back like this, and the angle that's made with the normal line. Now remember, normal again means perpendicular, so perpendicular to the surface, and I always recommend drawing the normal line first. So this incident angle here, theta I, is the same as the reflected angle, theta r, and that's the whole idea of the law of reflection. It's the same thing that would happen if a bowling ball or a billiard ball hit the bumper of a pool table or something like that. So what happens is when your eye sees this object, it assumes that the light travels straight, and so it thinks that the image is back over here. So in this case, whatever the distance between the object and the mirror is going to be the same as the distance between the mirror and the image. Now in this case, the light ray, that's the solid line, I always use solid lines to show light rays, the solid lines here don't actually travel to the image, right? There's no light ray that actually passes through this mirror. That's instead just where your eye perceives the image to be. So we're perceiving this then as what we'd call a virtual image, because the light rays don't actually pass through them. All right, so scooting right along here, speed of light is 3 times 10 to the 8 meters per second. The speed of light, this is the speed of light in a vacuum, and so this speed of light can change depending on what medium you're working in. This is the fastest that light will ever travel, and so whenever we see c in an equation, c is always going to be 3 times 10 to the 8 meters per second. Now, light is a wave, so it does follow the same wave equation that we learned before test 1. So v, the speed of light, can change depending on whatever medium you're working with. The frequency of the light does stay constant. Okay, so we'd think about this just the same way that we'd think about somebody oscillating a jump rope up and down or something like that. The oscillation frequency is the same, but the speed of the light can change depending on the medium, right? So depending on how heavy that jump rope is, the speed of the waves will vary. So v changes, but f stays the same, which means then if v is changing, lambda's got to change depending on the medium. We have a relationship to figure out what the speed of light in the medium is. N equals c over v. N is a special attribute called the index of refraction that we give to all sorts of different mediums that light can travel through. And it's just simply the ratio of the speed of light in vacuum. Again, that's hitting its limit, 3 times 10 to the 8th. That's c, always. V is the thing, the speed of light in that special medium. All right, scooting along further. So when light enters a medium, it changes speed. We just saw that with the previous equation, n equals c over v. So when light enters a denser medium, that is, when n is bigger, the light slows down. In other words, v gets smaller, and thus it bends towards the normal. And we saw that when we were talking about the lawnmower example and things like that. So here's the light, right? Let's say that it's traveling from low n, so maybe air or something like that. Air has an n value of 1. To a higher n value, such as water or something like that. So here's this laser. Notice that all of the angles that I'm measuring are measured from the normal. That is important, otherwise these equations won't work. So the light ray is traveling, it hits the surface of, let's say, the water in this case, and then thus bends towards the normal because it's slowing down. So we call this bending of the light refraction. And in talking about the equations that are involved, we would use Snell's law, n1 sine theta 1 equals n2 sine theta 2. Again, theta 1 and theta 2 have to be measured from the normal, otherwise it doesn't work. Make sure you're keeping your n1 and n2 separate. Usually we think about wherever the incident ray is, that initial ray, that incident ray is going to be in this, associated with subscript 1. and then whenever the ray is refracted, that's associated with subscript 2. All right, so this sort of covers the basis when you're going from low N to high N. This equation also works if that light ray were instead reversed, if we were going from high N to low N. But something really, really special happens when you move from high N to low N. Because you could imagine, for example, reversing the direction of these rays and swinging outward this theta, in this case, I guess it would be theta 1, this lower angle down here in the high N, to the point where your refracted ray actually skims along the surface between these two media. So in that case, when the light starts in the denser material, so let's say this is water and it's hitting air or something like that, when it starts in the denser material, you could potentially have a refracted ray because it's going to bend away from the normal. Your refracted ray could refract at an angle of 90 degrees. And if it does that, then you get this really special case. We call this initial angle, this incident angle here, the critical angle. So when the critical angles can only occur when going from a high N to a low N. Critical angles happen, we use the exact same Snell's law equation, n1 sine theta 1 equals n2 sine theta 2, but in this case our theta 2 has to be 90 degrees because we're in this special case where we're talking about the critical angle. So that light ray has to skim along the surface. So there it is, n1 sine theta 1 equals n2 sine of 90 is 1, and so then we can just solve for theta 1, which in this case would be our critical angle really easily. If we swing this out even further, if we swing out our incident angle any further, then all of the light will be reflected. And so this is why when you're in the pool and you're under the surface of the water, when you look off to the side, you almost see like a mirror effect at the surface of the water. That's due to total internal reflection. This is also how fiberglass optics work and things like that. So it's basically trapping the light inside the medium with a higher N value. Cool, okay, so we can keep cruising along here. Different wavelengths of light travel at different speeds in a medium. So they each bend at different angles, and this is how we get dispersion. This is the effect that results from a prism or from a rainbow and things like that. All right, lenses. Okay, so lenses. Let's talk a little bit about lenses briefly here. It's two different types of lenses that we talked about. You could have a converging lens or a diverging lens. When dealing with lenses, we said the trickiest part of these is dealing with the signs, sign S-I-G-N. So the sign of the focal length for a converging lens is always going to be positive. The sign for a focal length of a diverging lens is always going to be negative 100% of the time. So now let's actually, I want to go back over here for a moment if I could, and I'm going to show you, actually I'll start with a converging lens. So this is a simulation of a converging lens, and I will link to this in the Sakai folder on chapter 33. But here's an object, right? And so what you can see is, here I'm taking a converging lens. So a converging lens is just like a magnifying glass or something like that. If I look at an object from far away, so here this object, this arrow here, is out further from the focal length. So it's out past the focal length. Here, this little letter F here is showing us the focal length. So we're outside the focal length of this lens. Notice that the image is always upside down. We use the word inverted. And the light rays actually pass through this image, in which case it is a real image. So always, 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 no matter where I put no matter where I put the object, as long as it's out past the focal length, I will always get a real and inverted image. Real and inverted. Real again because the light rays are actually passing through it. Okay, now if I bring this object in, watch what happens. When I bring it in past the focal length, something strange happens. I'm going to bring it in a little bit further here. So here's this object. The object is now within the focal length. So, so now the light rays kind of bounce off in sort of a weird way. They actually diverge on the side of the lens, but our eyes still perceive the light rays as traveling straight through. So you can see here these red dashed lines are meant to represent basically virtual rays. So this image in this case is the result of virtual rays. So this is a virtual image. This is not a real image. And this image is upright. This is how a magnifying glass works. You take an object, you bring it close to the magnifying glass, and you see it big, and upright. So that is the idea of a converging lens. So I summarized that here. When you're dealing with a converging lens, you have two options. Either the object is outside the focal length, in which case you're looking at something far away, and so you see the image as inverted and therefore real. In fact, all images that are inverted are real. Or you have the option that the object is inside the focal length, in which case the image is upright, here's the image right here, and virtual. In fact, all upright images are virtual. These two adjectives are effectively synonymous with each other. All right, let's just talk briefly about the diverging lens. With the diverging lens, notice there's not two options. I can actually put the object anywhere. So let me flip back for a moment to the simulation. So here's the simulation. Here's my diverging lens. And again, this guy right here is my object. So here's the object. I can put it anywhere. Notice here I'm outside the focal length. And you can make out, hopefully, this really small image in there. So the image is upright. And it's virtual. Notice that it's dashed lines that, for the most part, that are forming that image. And so it's a virtual upright image. So that's still consistent because we said all virtual images are upright and vice versa. And then if I bring it inside the focal length, nothing really weird happens, right? It's basically the same image. It's still upright and it's still virtual. So flipping back to the simulation, or to the summary rather, here our image is always upright and virtual. All right, now we want to put some quantitative tools to this new lens idea. So we have the lens equation, 1 over f equals 1 over do plus 1 over di. For our purposes, the object distance is always going to be positive. We always consider wherever the object is to be basically the front of the lens, and so that would be positive. Di is positive, basically if you have a real image. In other words, if your image is on the opposite side of the lens from the object. So let me flip back up here. So here, for example, when we had a converging lens with the object outside the focal length, the image was appeared on the opposite side of the lens from the object. Therefore, in this case, our di would be positive. When we had a converging lens with the object inside the focal length, however, the image appeared on the same side of the lens as the object. Therefore, our di would be negative. And we are dealing with a virtual image there. Okay, so there's our lens equation. And we said f was positive for converging lens and f is negative for diverging lens. We also have the magnification equation, which is fairly straightforward. All right, so that summarized our ray optics. Let's just take a few minutes to summarize our thermal interactions as well. The first thing that we started with was just conservation of energy. So last semester we talked about how the changes in our total energy have to come from somewhere. And the only thing we had talked about at that point was mechanical work. In other words, somehow applying a force to our system could therefore change like the kinetic energy or the potential energy or one of these other energies for our system. But now we're introducing the idea of heat. So we can also heat a system like this. You can put a pot of water on an open flame, and then the water will eventually, we'd say, heat up, right? Its temperature increases. So to show that its temperature increases, we say delta E thermal is positive. And to account for that change in thermal energy, we'd say, well, it made contact with something hot. And so that is referred to as Q. And so Q here would be positive. So our delta ETH is positive and our Q is positive. Notice that this satisfies the conservation of energy equation. Here, if I take up all these bars, all these changes in energy here, most of them are 0, all these bars have to add up to some positive number, and that has to equal the sum of the work and heat. So sum of work and heat equals some positive number, sum of all of our other energies equals some positive number. All right, excellent. So they're equaling the same thing. Now we could, alternatively, we could have heated up our system instead of just putting it in contact with something hot. We could do work to our system. And the classic example here is a gas inside of a piston. So you can apply a force to this piston inwards. The force is in the same direction as the displacement of the piston, so therefore you're doing positive work on the system. So our W is positive, and this causes all of these little air molecules or whatever gas you have in here to bounce around faster, which means that you've increased the thermal energy of the object or of the system. Now, some people have asked, why don't we say that that's an increase in kinetic energy? Because it's actually not an increase in kinetic energy of sort of the macroscopic system as a whole. We use kinetic energy exclusively to talk about macroscopic systems, and we use thermal to talk about kinetic energy of particular air molecules, and so this would be an example of thermal energy increase. So in this case, we've actually heated up our system, but we haven't added heat to our system, right? We've increased the temperature, I should say, of our system without adding heat to our system. So in that case, when Q equals 0, anytime Q equals 0, the process is referred to as adiabatic. All right, we also talked a little bit about work done on the gas, how you could quantify that, how you could actually find that. You'd have to be given some information about pressure and volume. So taking just a one-step process, let's say, that starts over here at this point and goes over here to this point. Notice the direction of the arrow does matter here. All you would need to do to find the work done on the gas is find the area under this curve. Now in this case, the arrow is pointing to the right, so this would be a positive area under the curve. But then you need to stick a negative sign in front of it. And again, just like with optics, we have to be really careful about our signs here. So the work done on the gas is negative the area underneath the PV curve. So here, let's see, I had a width of 9 and a height of 10, and so there's my area. And then I had this extra negative sign just coming from the equation for work done on the gas. So in this case, that's negative 90 joules. If I wanted the work done by the gas, it would just be the opposite of that. So in this case, it would just be plus 90 joules. Now let's say that you instead had a process that went the other way, that maybe started at 10 meters cubed in volume and then went to 1 meter cubed in volume. So here you're actually compressing the gas. So in this case, you're doing positive work to the gas. So hopefully it makes sense, right? You're pushing in that piston. So here the work done on the gas is going to give us a positive number. And so to account for that, we basically just say, oh, well, this area is pointing to the left, so the area itself is negative. We still have that negative hanging out in front, just like we did before, and those two negatives cancel to give us a positive number. So everything checks out. So here, the work done on the gas was negative because the work was done by the gas. The gas was the thing expanding. Here, the gas is compressing, so we had to have done positive work on the gas. You can combine these two. So what if I had the first process and then I did something and then I did the second process, right? So now you've actually created a loop like this, and this should be another PV diagram. Sorry, it's a little bit hard to write with the trackpad, but hopefully you get the idea here. So this is another PV diagram. Well, this is just the total amount of work done in process 1 plus the total amount of work done in process 2. So I just take those two values. If I want to find the work done on the gas here, I would just take the two work-ons and add them up, and so I get negative 72 joules. So what we said was, okay, this is a clockwise rotation. The work done on the gas for any clockwise rotation will have to be negative, just because of these reasons that we just talked about. Okay, moving off of that and into heat. When you heat a substance, it can have two effects. You can either increase its temperature, in which case you'd use Q equals mc delta T, or you can literally break up the bonds that are holding that substance together, so you can change the phase of the substance. In other words, you can change it from a solid to a liquid, or from a liquid to a gas. You can only do one or the other. You cannot do both simultaneously. So what does that end up looking like? So here, for example, if you started with ice, really, really cold ice that's below the normal freezing point for ice, so let's say it's at negative 20 degrees Celsius. So if you start with ice down here and you put your ice in a pot and you put a flame under it, then what's going to happen is the ice is going to increase temperature. That's the first thing it's going to do. And so during this process, you're going to use Q equals mc delta T to determine how much heat is required to increase the temperature of the ice to, say, 0 degrees. Because right at 0 degrees, something special happens with ice. It starts to melt. So we figure out how much heat that takes to bring us up to the melting point of ice. And then we say, all right, Well, now let's melt the ice. How much energy does that take? So we're going to melt the ice. Notice that we're not changing temperature here. We're staying at 0 degrees the entire time that we're melting the ice. So you're going to end up with kind of a slushy type material in here. But when you're doing that, you're going to use this Q equals MLF equation. This is the latent heat of ice. You'd have to look that up or something, but presumably they would give that to you and perhaps the mass of the ice, and you'd have to determine then how much heat or how much energy is required to melt the ice. Okay, so you do that in the second process. Let's say you want to keep increasing the temperature of what is now water. So now you have water at 0 degrees right here. You want to increase its temperature. So you're going to use Q equals MC delta T again, and this time you're just going to strictly increase its temperature. Now we're doing all this talking about temperature. When you have delta T in an equation, you can use either Celsius or Kelvin. Either one is fine because they both have the same size. But you cannot use Fahrenheit. Fahrenheit has a different size, and we have a means of converting between Fahrenheit and Celsius using this equation right here. We also have a means of converting between Kelvin and Celsius. When in doubt, Kelvin will always 100% of the time work. Kelvin is our SI unit. Sometimes it's just more convenient to keep things in degrees Celsius when you're working with just changes in temperature. But again, if you're ever doubting yourself, Kelvin's the way to go. All right, just a couple more things here. We talked about heat transfer methods. There are 3 of them. The first one is called conduction. This is literally when you take a hot object and you put it in contact with a cold object. What we talked about specifically was, like, for example, you had that mini lab where you had a cube of aluminum or brass or copper that you held in your hand. So in that case, your hand was transferring heat or transferring energy thermally to the metal cube. We could also talk about it in terms of a house, right? So here's the inside of your house at a nice warm temperature. Here's the outside of your house at a nice cold temperature. There's some distance in between the two and some kind of a separation of some kind of insulation to keep your house warm. But you can still discuss the rate of conductive heat transfer because there is still heat going out of your house. Hopefully not a lot, but it does happen. So there's a rate of conductive heat transfer here that'll be based on the thermal conductivity of whatever material you're working with, so you'd have to be given that or look it up in a table. Surface area, that is literally the surface area of, in this case, your house, or if you're dealing with the block, you would be talking about the block. This is the difference in the temperatures, again, because this is just change or a difference in temperatures, just straight up T2 minus T1. You can use Celsius here. And then thickness, this is the separation between T1 and T2. That is just going to be the thickness of the walls. Now, in the case of our mini lab, we used the smallest parameter divided by 2 in that case because you had, you had your block here. Sorry, I'm doing my best. So you had your block, and we thought about the center of the block as maintaining its room temperature. And so the separation then between your hand and the center of the block in that case was actually the width of your cube divided by 2. That was a very special case. That is not usually the way things work. Usually it's just strictly the thickness of whatever insulating medium you have. All right, number 2, we talked about convection. There weren't any equations that we talked about involved with convection. Convection is simply the large-scale flow of matter that causes change in temperatures. This can only happen with fluids, that is with liquids or gases, because it's literally a mixing of molecules. So when you stir your creamer into your coffee, that's a really beautiful example of convection. And then finally, the last one that we talked about was radiation. This is when some sort of a hot object emits electromagnetic waves. And so you actually have heat radiating off of a body. It could be a human body, it could be the sun, it could be literally any hot object. It could be a radiator. That's why it's called radiation. So what is the equation then for heat transfer by radiation? So remember this Q over T, and I should have mentioned this previously too, because the same thing was true up here when we were talking about conductive heat transfer. Anytime that you divide something by T, you're talking about a rate. And so here, this left side of the equation is the rate of heat transfer by radiation. Sigma is just a constant. It's going to be 5.67 times 10 to the negative 8 joules per second, meters squared, Kelvin to the 4th, every single time It's going to be that constant. E is the emissivity. That's basically how well the object radiates. That's going to be some number between 0 and 1, and you, again, have to be given that or look it up on a table, unless that, of course, was the thing that you're looking for. And then surface area is just literally the surface area of the hot object that is transferring the heat via radiation. And then T2 and T1. So T2 would be your environmental temperature. T1 would be the temperature of your object, or vice versa. It doesn't actually matter, as long as you're clear about what the sign of the heat should be. In this case, the person is radiating heat, as I've drawn it, and so they have a negative Q associated with them because Q, or energy in the form of heat, is leaving their body. So they'd have a negative Q and their environment would have a positive Q. But sometimes it can work the other way around. Perhaps the environment is hot and the person is cold, in which case then the person would be receiving that energy thermally, so it would be positive Q. So just be careful about your signs always. But as long as you're thinking about it in terms of the energy diagrams, you should be all set. All right, excellent. I hope that this video was helpful, and I'll look forward to seeing you on Monday.